Today we are going to talk about a couple of different topics that are related to each other. The first of which is the topic of source transformation. So, in order for us to perform a source transformation, we need to understand the concept of electrical equivalence, which is something that we've been working with for the past several weeks. I don't know if I've used that terminology directly, but let's say that we had the following circuit where we had some voltage source connected to a resistor network where we saw two resistors, R1 and R2 in series. This network is electrically equivalent to a voltage source connected to a single resistor where that single resistor has a value of R1 plus R2 from our original circuit. Right, so all I'm saying here is that we can replace that resistor R1 in series with resistor R2 with a single resistance having the same value of that sum, and the two circuits would be electrically equivalent, right? So one of the ways to ensure electrical equivalence is that the voltage drop across our terminals, let me put the VS here because I forgot it, needs to be the same, and the current either entering or leaving the terminals needs to be the same, and the power absorbed or supplied by the network needs to be the same in both cases for both circuits to be electrically equivalent. It's fairly easy to prove here, right? So we know that the voltage drop, VL, in this case, would be whatever IL is plus R2. IL would simply be VS divided by R1 plus R2. And so the power absorbed by our load would be VL times IL, which would look like VL is expressed in terms of IL, so I'll put an IL here, R1 plus R2 times VS over R1 plus R2. And then substituting in for IL again here, we're going to have VS divided by R1 plus R2 times R1 plus R2 times VS over R1 plus R2, ultimately giving us a power of VS squared divided by R1 plus R2. Over here, we're going to have literally the exact same relationships. VL is equal to IL times R1 plus R2. IL would be equal to VS over R1 plus R2, and so forth, we can easily see that we're going to come up with the exact same expression, right? So, in a nutshell, two circuits are electrically equivalent if they have the same voltage drop, the same current, and the same power. So what we're going to look at are practical sources. So let's say that I have a voltage source in series with some resistance RS, like so. And I have a current source IS in parallel with some resistance RS, like so. And both of these networks are going to be connected to an arbitrary load resistance RL, so that here's my voltage drop VL, here's my current IL. So what we're going to figure out today is what are the conditions that I can replace this practical voltage source. So let me write this down here. With this guy right here, which is what's called a practical current source. There are specific conditions to where these two networks are electrically equivalent to each other, which means we can replace one with the other without losing any information about our circuit whatsoever. Okay. So if we look at our left-hand circuit, we could see that the quantity VL would be VS times RL over RS plus RL using voltage division. We could see that IL would be equal to VS divided by RS plus RL. On the right-hand side, if we wanted to find that voltage VL, we could use Ohm's law. And we would have IS times the parallel combination of RS and RL. So that would mean RS times RL over RS plus RL. And to find IL directly, we could use current division. So that would be IS times 1 over RL divided by 1 over RS plus 1 over RL. And this is going to be the same thing as IS times RS over, RS plus RL. So my question to you guys is, what is the condition for which these two circuits are electrically equivalent? So what needs to happen in order for VL on the left-hand side to equal to VL on the right-hand side and IL on the left-hand side to equal to IL on the right-hand side?
just a quick shot, would IL need to be the same? The problem, the hesitation there is that IL isn't in, or IS isn't in the bottom left equation.
So the goal here is for IL to be the same thing on the left-hand side and the right-hand side, and for VL to be the same thing on the left-hand side and the right-hand side. So let me help you guys out here a little bit.
Is it VS equals ISRS?
That's 100% correct. You nailed it. All right. So when VS is equal to IS times RS, these two circuits are electrically equivalent to each other, which means we can replace a practical voltage source with a practical current source under this constraint, or we can replace a practical current source with a practical voltage source under this constraint. So let me go through the rules here really quickly, now that we've figured out under what conditions these guys are electrically equivalent, okay? So let's say that I'm going to convert from a voltage source having a value of VS connected in series to a resistor RS. And I want to convert this into a practical current source. So the value of my current source will simply be whatever VS is divided by RS, using simple algebra there. And then my resistor RS does not change, but it's now oriented in parallel with the source. One thing that I do want to point out here is that the positive polarity terminal of our voltage source is going to be on the same side as the head of our arrow for our current source, right? So if the positive polarity is on top, then the current is going to flow up. If the positive polarity terminal is on bottom, the current's going to flow down. The positive polarity terminal is on the right, the current's going to flow to the right. Positive polarity terminal is on the left, the current's going to flow to the left. And then we can obviously go in the opposite direction as well. So if we had a current source in parallel with a resistor RS, we could then convert this into a voltage source in series with a resistor RS under the constraint that our voltage source has a value of IS times RS. So what we're going to do here, because this conceptually isn't particularly difficult, but it's interesting to see how it can come into play, right? Or how it can be utilized. So I'm going to draw a circuit here. Let me find the one I want to look at. There we go. And it's going to be a fairly gnarly looking circuit. So let's start with a 5 amp source down here. Let's put this in parallel with a 3 ohm resistor. Let's place a 4 ohm resistor here. Seven ohm resistor here. There's a 3VX current source in parallel with a 17 ohm resistor up top. Two ohm resistor over which our voltage drop VX is defined. Here's a 9 ohm resistor. And here is a 1 amp source. So if our ultimate goal in this circuit was to solve for the voltage Vx, before we had learned about source transformations, we might be inclined to do nodal analysis or mesh analysis for this problem, right? So by inspection, I can see that there are 5 meshes, which means this would be a solve it using a computer style problem. And I can see that there are, let's see, 1, 2, 3, 4, 5 nodes. So also probably have to use a computer to solve it, unless we happen to have a Casio 991. Since we're going to choose one of our nodes to be a ground node, that'll be give us a 4-equation 4 unknown system. So for many of us, solving this using our current level of circuits knowledge would require the use of a computer. Let's see what happens though if we use this technique of source transformation in order to simplify our circuit here. So the first thing that I'm going to do is I'm going to draw a dashed line here. And what I'm going to do is I'm going to replace everything to the left of this dashed line with its electrical equivalent. So I have a practical current source here on the left, so I'm going to replace it with the following practical voltage source, and I'm going to draw this out so that we're all on the same page. So my conversion is going to look like 5 amps in parallel with 3 ohms. Will become 5 times 3 is 15, so 15 volts. In series with 3 ohms. So I'm going to make that change here. How I like to do this is effectively I completely disconnect the network and then replace it at the terminals with the electrical equivalent, which in this case would be 15 volts in series with 3 ohms. So what did that operation do? Well, it actually eliminated one of the meshes, right? We went from 5 meshes down to 4 meshes, but it also introduced a node, right? Because this node right here did not exist because it was tied to a short circuit a moment ago. That being said, that 3 ohm resistor and the 4 ohm resistor, which could not be combined earlier, are now they appear as if they're in series, which means we could just add the 3 and the 4 together to give us 7, right? So I can erase this 4 ohm resistor here and make this a 7 ohm resistor, and I got rid of the node that I just introduced by doing that source transformation. Okay. So this is another way for us to work through resistor combination techniques and all that kind of stuff as well in the presence of voltage sources and current sources in specific configurations. So what we could do now is we could take this practical voltage source that we just made, the 15 volts in series with the 7 ohm resistor, and convert this back into a current source. So 15 volts in series with 7 ohms is electrically equivalent to 15/7 amps. In parallel with 7 ohms. And so I am going to disconnect this practical voltage source and replace it with an electrically equivalent one. So this will be 15/7 amps in parallel with 7 ohms. And now, by doing this particular source transformation, I've put these two 7 ohm resistors in parallel, which means I can combine them, right? So 7 in parallel with 7 is what?
(49/14).
3.5.
3.5, yeah. So whenever you have two equal resistors in parallel, the equivalent resistance is just half of whatever the resistor value was. So 49/14 is correct, but that is the same thing as 3.5 or 7/2. So I'm going to put 7/2 here. And erase that resistor. I'm going to come back and I'm going to wind up doing another source transformation on this thing to the left of the right dashed line here in a moment, but now let's leave it alone. Okay. So let's look at what we've got right now. So we have 1, 2, 3 nodes plus assuming the bottom node is ground, or we have 5 meshes. So we're at a point where we could do nodal analysis, but this can actually be simplified further. So let's just keep on trucking with this here. So I am going to convert everything to the right of this blue line into its electrical equivalent as well, right? So if I have 9 ohms in parallel with 1 amp, that is electrically equivalent to 9 ohms in series with 9 volts. Roll up here. I want to look at something else here really quickly. So even though we have a dependent current source here, we can still treat this thing above the purple dashed line source because it is a current source in parallel with a resistance, okay? So I could replace that network. Let me draw it out here. My stylus were right, there we go. With an electrically equivalent network that would contain a practical voltage, or excuse me, a dependent voltage source. In series with a 17 ohm resistor. So because the head of my arrow is to the right, the positive polarity terminal is going to be on the right, and 17 times 3 Vx is just going to be 51 Vx. Now the last thing I'm going to do is do that source transformation more time like I talked about earlier on. I'm going to tuck it in here over to the right. So if we have 15 over 7 amps in parallel with 7/2 of an ohm, that would be the same thing as 15/2 of a volt in series with 7/2 of an ohm, making that replacement. We took that big, ugly original circuit, which had 5 meshes and 5 nodes, and we converted it using a lot of source transformations. Don't get me wrong, but we used source transformations to turn that into a single loop circuit that we could have analyzed on the second day of class, right? So from here, just as a quick refresher, my stylus will change colors. Let's assume that our current I is flowing around this loop in this direction. We would have negative 15.5 volts plus, I'm sorry, this was supposed to be 7/2, not 15/2. That's my fault. 7/2 of an ohm times I minus 51 Vx plus 17 ohms times I plus 2 ohms times I plus 9 ohms times I plus 9 volts is equal to 0. And using Ohm's law, we could see that Vx is just 2 ohms times I. We have a single equation with one unknown quantity. Solve, 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 and we can get the answer that we're looking for, right? So for you guys right now, this is just really another tool to add to your toolbox to utilize in order to simplify a circuit down into something a little bit easier to deal with. I fully understand that most of you probably wouldn't go through the 1, 2, 3, 4, 5 different source transformation steps here to bring this down to a single loop circuit. You could stop after 1 or 2 steps when you had it solvable by using either nodal analysis or mesh analysis. And that's perfectly reasonable thing to do. But what I want to talk about now is the maximum power transfer theorem, which requires us to effectively understand that in specific instances, we can reduce a circuit down to effectively a practical voltage source or a practical current source, which we can effectively do with this one. Okay. So let's do this here. So I want to take a circuit. Let's do this one here, where we have 12 volts in series with a 3 ohm resistor in series with a 6 ohm resistor in series with a 7 ohm resistor, and finally in series with some resistance here, RL. And I want us to use source transformations in order to break this circuit down into a simplified form here, where we have some source voltage in series with some source resistance in series with some load resistance, RL, like so. So I want us to break this thing down or simplify it to a point where we have a simple single loop circuit. Okay. So you guys walk me through what's going to happen. Tell me what the first transformation would look like.
We would transform the voltage source into a current source on the left.
Okay, so the current source would have what value?
Is it 36 amps? Multiplying 12 by 3?
So you would divide 12 by 3. So if we scroll back up here, VS will be equal to IS times RS. So IS will be equal to VS over RS.
So then there would be 4 amps.
Okay. So 4 amps. Would the direction be up or down?
Up.
Up. Okay, I agree. Because the positive polarity terminal is on top, the direction will be up. And that'll be in parallel with 3 ohms. And then I'm going to draw the rest of the circuit here. All right. So what would my second step look like? What can I do now to simplify this
3
thing?
and 6 ohm resistor because they're parallel.
All right, so the 3 and the 6 are in parallel. So what's 3 in parallel with 6?
Three. Oh, I'm sorry, 4.5.
I disagree.
2,
2.
18 over 9.
Yep, 18 over 9 is 2 all day long. All right, so what could we do now?
Transform the 4 amp source into 2 ohm resistor.
Okay, so what's that going to give me?
8 volt source, positive up, negative down, yep. And then a 2 ohm in series with both the 4 amp and the 7 ohm. And then we were going to combine those two, I assume.
Yep, we're going to combine those 2 resistors. You're absolutely right. Let's do it step by step here. Here's RL. And then lastly, as was suggested, we'll combine the 2 ohm resistor and the 7 ohm resistor to give us a single in series. Okay. So we did all of that work here to convert this larger circuit into a simplified representation where we have a practical voltage source connected to our load resistance. We could also wind up with a practical current source connected to our load resistance as well, which we can obviously see just by doing a simple transformation here. This is arguably just as simple. 8/9 of an amp in parallel with 9 ohms in parallel with RL. Okay. So the purpose of doing this simplification is to make it easier for us to determine the power absorbed by our load resistor, right? So we could easily figure out what VL is, or the voltage drop across our load resistor, or the current flowing through our load resistor using this simplified representation. And I'll draw it here as well. So we could use power absorbed by our load resistor would just be VL squared over RL, where VL squared in this case would be 8 volts over 9 ohms plus RL squared times a factor of 1 over RL. And over on this side, we could do IL squared times RL, where IL squared is going to be, excuse me, 8/9 of an amp. Oh my gosh, can't write today. Times 1 over RL divided by 1/9 plus 1 over RL squared times RL, right? So the power analysis would be easier to do if the circuit were more simple, is what I'm getting at here. How could we figure out the maximum amount of power that is absorbed by that resistor RL? So that's all the maximum power transfer theorem really tells us, okay? So let's back things up here very slightly and look at a generic circuit. So if I have a voltage source in series with some source resistance RS in series with some load resistance RL, like so. Here's the voltage drop across RL, and here's the current flowing through RL. We could say that the voltage drop across our load resistance is going to be VS times RL divided by RS plus RL using voltage division. We could say that our current IL is going to be VS divided by RS plus RL. And from this, our power would be VL times IL, which is going to look like VS squared RL over RS plus RL quantity squared. So as a function of load resistance, PL would look something like this. So here's PL on the vertical axis, and here is RL on the horizontal axis. And we would wind up with a plot that looks something like this, where way over here on the left-hand side corresponds to when our load resistance is a short circuit, right? So if our load resistance is a short circuit, the voltage drop across it is 0, which means it should be absorbing 0 power. Okay, so that represents the leftmost extreme of the graph. On the right-hand side, we're going towards infinity. Well, when RL is equal to infinity or an open circuit, no current can flow through, and so there will be no power absorbed either. And then for all resistance values between a short circuit and an open circuit, we should see that our load absorbs some amount of power. Well, there is one specific value of RL where the power absorbed is at a maximum value. How would we figure out what value of RL causes maximum power to be absorbed? So how do we find the maximum value of this power function?
Would we have to take the derivative?
Take the derivative and set it equal to 0. Absolutely right. So the derivative of PL with respect to RL is what we're doing. So that's going to be the derivative with respect to RL of VS squared times RL over stylus is being difficult, RS plus RL squared. So I'm going to approach this using the quotient rule, right? So because I can never remember what this actually is, give me just a moment to toss it into Google. Quotient rule for derivatives. Just to be clear here, the derivative with respect to x of f of x over g of x is equal to g of x times the derivative of f of x with respect to x minus f of x times the derivative, sorry, that is definitely a q, not a g, g of x with respect to x. All of this is divided by g of x quantity squared. Well, our numerator here is our f of x and our denominator here is our g of x, right? So we're going to have a g of x term, so that is rs plus rl squared. What is the derivative of the numerator with respect to RL?
VS squared.
Yep. All right, and then we're going to have minus our numerator, so that's VS squared times RL. And then what's the derivative of our denominator with respect to RL? Anybody?
I'm not sure.
So I believe, I might be mistaken here, but this is a simple application of the chain rule. Right? So the derivative of that whole thing would be twice RS plus RL, and then we're only looking for, if RS is a constant, that's just going to give us 2RL. If I'm remembering how to do that calculus correctly, which we'll find out here in a moment. And then I'm going to have my denominator squared. So that's going to look like RS plus RL to the fourth power. And we want this thing to be equal to 0. So if we want this thing to be equal to 0, all that really means is that the numerator needs to be equal to 0, right? So I can go a step further here and say that RS plus RL squared times VS squared minus twice VS squared RL squared is equal to 0. My VS terms are going to go away. So this is going to look like RS squared plus twice RS RL plus twice RL squared minus twice RL squared is equal to 0. This term and this term cancel each other out, and I'm concerned that I've made a mistake when I took the derivative of this. So let me double check that really quickly. I feel like a jackass for not knowing how to do that off the top of my head, but it'll be okay.
You might be missing like a +1 or something.
Yeah. So I did make a mistake. Instead of it just being twice RL, it should be twice
Statement.
RS plus RL. So I apologize. Oops, sorry for that. Yeah, I had an extra term in there that was going to give me a negative answer, which is why I started freaking out. So let me fix this here. I apologize for the math mistake. So let's see. So the twice is going to come out. Then I'm going to have the VS squared, and then I have RS RL plus RL squared. If my mental algebra is correct, which is highly suspicious, so let's double check this here. So the 2 gets multiplied through by everything, so that's why I took it out. The VS squared gets multiplied through by everything, so that's leaving me with RL times RS plus RL. So I should have an RS times RL plus RL times RL. So I think that's right. The VS is cancel. let's go back to this thing. So when I FOIL this out, I have RS squared plus 2RS plus RL squared minus 2RS RL minus 2 RL squared is equal to 0. Let's look at this now. So this guy cancels this guy. That seems good. This guy is going to get rid of one of those. And so what I'm left with, and this is working out right now, is RS squared minus RL squared is equal to 0. So this means that whenever RL is equal to RS, PL will be at its maximum. So let's put RS here. Substituting in, so P max occurs when RL is equal to RS. So we had our equation that it was VS squared times RL over RS plus RL quantity squared is going to look like VS squared times RS over twice RS squared, or 1/4 VS squared divided by RS. So this is our maximum power relationship for a practical voltage source representation of a circuit. If instead we had a current source or practical current source representation, this would just be 1/4 IS squared times RS. So effectively, if we can break any circuit or simplify any circuit down to a practical voltage source or a practical current source connected to some load resistance, we can then use the maximum power transfer theorem in order to calculate the maximum amount of power that an arbitrary resistor RL can absorb. So using this information, let's go back up here for this example. Okay. What value of RL will cause that circuit to deliver maximum power to that resistor RL?
RS, right?
Which is
Which is
8
9
volts.
ohm.
9 ohms, the only resistor that isn't RL. Absolutely right. So
What-
if
where did he get that from again? Okay. Okay.
so
that's
what
not
we so what we did is we took this original circuit and we simplified it down to literally a practical voltage source in series with that resistor RL. So the only resistance that has a value, right? So this right here is VS. This right here is RS. So if RL is equal to 9 ohms, then max power will be transferred.
okay.
And the value of the maximum power is just going to be 1/4 times 8 volts squared divided by 9 ohms, which is 64 over 36. I know that can be simplified, but I'm going to be lazy and leave it as that. So a little less than 2 watts. All right, so what I want to do here really quickly, just to recap things, is work an example problem or two from your old tests. By the way, this is the last material that will show up on exam number 1. So let me pull open some of the old test files here really quickly. Open the folder. Old tests. Let's look for exam 1. Let's do this one. Let's see what we got here. It's going to be effectively some of the last problems on the exam because it's the last material that we covered.
So what you're saying is that like all the way up to this class is going to be on the test?
Yes.
Okay, that sounds good.
Yeah, so we are going to have a lecture on Thursday, but the material that we cover on Thursday will not be on the exam. It can be used if you choose to do it, but you're not going to be directly tested on it. So this circuit right here, following circuit will be used for the next 2 problems. There's a resistor RL here, so a resistor where you're not given the value, that's probably going to be the biggest indicator that you're supposed to do what we covered today in class. So our goal for this particular circuit would be to simplify this down into either a practical voltage source or a practical current source representations. So let me redraw this circuit, and then let's talk our way through that. So we have an 11-volt source over here on the left. And then we had, I think it was an 18 ohm resistor and then a 2 amp source. Uh, 11, 14, and 7. And I believe over here, we just had our resistor RL. The first part of the problem. This is CL and IL. And let's look here. Yeah, so the first part of the problem is simply asking us what value must RL have so that the circuit absorbs maximum power. So effectively, what it's asking us to do is replace everything to the left of this dashed line with either a practical voltage source or a practical current source. If we have either of those representations, whatever resistance that we have is the answer to that problem. So what can I be doing here? How do I simplify this down?
Would you convert the 11 volt on the left to a current source first?
Okay, so we can definitely do that. So that's going to look like 11 over 8 11 over, yeah, 18. My apologies.
And then that would go in parallel with
18. $11. 14. 7. Here is our RL. Okay, so what can we do now?
Combine current sources.
Okay, so what's that going to look like?
I think 47 over 18 amps.
Yeah, so 36 plus 11 is 47. So 47 over 18 seems good to me.
And I am so sorry, but where is the 47 coming from? It's 47 times.
2 plus 11 over 18.
Okay, got it.
And I'm just doing 36 over 18 as 2.
Thank you.
What would we do now?
Could you solve 11 and 14 in parallel and then convert the 7 volts to a current source?
So the 11 isn't in parallel with 14 or 18 for that matter.
At this point, we can either do the current source or the voltage source transformation and then start combining stuff.
So let's do the current source transformation. Actually, let's do the voltage source transformation first. So we're going to have that 47 over 18 still. The reason why I'm choosing to do the voltage source one first is because I want to be explicit about where that practical source is going to show up here. Because my concern, based on how I've seen students try to do this in the past, is that you guys aren't always great with this particular configuration. So the 14 ohms in series with the 7 is between this node and this node. So I want to make sure that my equivalent is still between those same 2 nodes. And so to me, that's going to look like 7 over 14 is half. So half of an amp in parallel with 14 ohms like this. And then over here is my resistor RL. So doing that source transformation, which is absolutely going to be an integral step, until we do the source transformation and some other simplification on what we have on the left-hand side, doesn't actually let us really do anything. The 14 ohm resistor still isn't in parallel with the 11. It isn't in parallel with the 18. The 11 still isn't parallel with the 18. The 1/2 amp source isn't in parallel with the 47/18 amp source. So there obviously needs to be something else that we need to do. So that something else is the transformation on the practical current source on the left. So 47/18 times 18 is just going to look like 47 volts in series with 18 ohms. This is going to be in series with the 11. Here's our 1/2 amp. Here's our 14 ohms. Here's our RL. I'm going to do 2 steps in one here. So obviously the 18 and the 11 are going to combine into a 29 ohm resistance. And then if we do a source transformation on the practical voltage source, we're going to wind up with 47/29 amps in parallel with 29 ohms in parallel with 1/2 amp in parallel with 14 ohms, finally in parallel with our resistor RL. And so now we would combine the 2 resistors and we would combine the 2 current sources. So let's see, 47/29 plus 1/2. I'm going to do that in a calculator. (123/58). And then 29 times 14 is going to look like 406/29 plus 14 is 43, if I'm not mistaken. And now we have our circuit down to a practical current source representation. So what value of RL causes maximum power transfer to occur?
406/43.
Absolutely right. So 406/43. 9.442 ohms, just for the sake of argument. Let's look here. Yep, there we go. And then the maximum power that can be absorbed by RL would be P max is equal to 1/4 times 123/58 amps squared times 406/43 ohms. .613 watts. What did I screw up? Let me check my handwriting here.
think your amperage might be wrong.
So let's see, 47 over 29 plus 1/2. 123 over 58. So 1/4 times x squared times 406 over 43. Let me just type this in. 29 times 14 over 29 plus 14. Yep, 10.616. So I think I just typed something into the calculator wrong. That being said, there's always the possibility that I've made a mistake on the exam. Because as you guys are well aware by this point, I make mistakes fairly regularly. If I make a mistake on the exam, what I usually do is wind up throwing that question away, meaning that everybody gets full credit for that question. So you're not necessarily wasting your time. I try to make sure there's as few mistakes as possible, but it's just me writing 6 versions of the test, so mistakes are going to happen every now and then. So anyway, I try to be fair about it. If I made the mistake, you guys shouldn't be penalized for it for sure. For part 3 of this problem, which just to be clear here, on the test that I'm giving you guys, my intention is literally to have something just like this one and then just like this one. Determine the value of RL for that causes maximum power transfer to occur, and then what is that maximum power? For this problem 29 here, I ask you, what current IL flows if RL is 13 ohms? So that's fairly straightforward. Sorry, that's the wrong thing. Effectively, we would just have 123 over 58 in parallel with 406 over 43 in parallel with 13 ohms. And we're trying to find this current IL. So how would we do that efficiently?
Current division?
Absolutely right. So if I have a current source in parallel with resistors and I'm trying to find a current flowing through a resistor, this is screaming for current division to be done. So that would be IL is equal to 123 over 58 amps times 1 over 13 ohms divided by 43 over 406 plus 1 over 13. Which I get to be 861 over 965 or 0.892 amps. Just to check things here, 892 milliamps is the same thing as 0.892 amps. So, yeah. So that example problem there, or that problem from that previous test, is very representative of what I'm going to ask you to do on the following exam, and you'll see that if you look at the other practice exams as well. It's just going to be what value of resistor causes maximum power transfer to occur, and then what that maximum power is. So if that example made sense and the previous example that we worked made sense, then you're good to go for this material. I think there are a couple of little things that look odd in the web work, so I want to look at them really quick with you. I may be misremembering, so I just want to touch on this really quickly. So this would be homework number 8, if I'm not mistaken. Let's look here. Nope, that one's fairly straightforward. That one's fairly straightforward. So this guy right here, I get a whole heck of a lot of questions about, so we can talk about it pretty quickly here. I'm not going to go through it per se, but I'm going to give you guys some strong hints. So homework number 8.3. Let's just look here at what we're given. So we're told that we have a practical DC voltage source can provide a current of 6.5 amps when it is momentarily short circuited. Okay, so I'm going to draw a circuit that describes that. So we don't know what VS is. We don't know what RS is. When the circuit is short circuited, our current IL is 6.5 amps. So from this information, I can see pretty easily that VS over RS must be equal to 6.5 amps. So that's one relationship. It can provide 83 watts of power to a 20 ohm load. Okay. So still don't know what RS is. But when this resistance is 83 ohms, PL is 20 watts, if I'm remembering correctly. Nope, I got it backwards. 83 watts to a 20 ohm load. Here is our current IL. So we know that PL is going to be equal to IL squared times RL. So that means IL is going to be the square root of PL over RL, and IL will also be, in this case, VS divided by RS plus 20 ohms. So we have one relationship here, a second relationship here. Solving this system should allow us to determine what VS and RS are. Okay. So once we know what VS and RS are, we want to find the open circuit voltage of our practical DC voltage source. So let's talk about that really quickly. So if I have voltage source in series with a resistance RS, my open circuit voltage is the voltage drop that appears at the open circuited terminals. What should this be? Let me
Just
ask-
VS.
Okay, absolutely right. Just VS. Why?
Because that's the only drop we have across that section.
Okay, so you're correct. The voltage drop across the resist RS is going to have to be 0 volts because there's no current flowing through it because it's open circuited. So if we wrote a Kirchhoff's voltage law equation around this loop, we would have negative VS plus VOC is equal to 0, which means VOC is equal to VS. So intuitively, it makes sense, but fundamentally, it also works out that way. Right, so that's part A. Let's see what part B asks of us. We want the maximum power it could deliver to a well-chosen RL. That's straightforward. P max is equal to 1/4 VS squared divided by RS. C, the value of RL, well, RL is equal to RS. So that one's fairly okay. If we look at this next problem, this is the one that really perturbs you guys. Because we have to do a whole heck of a lot of work to even figure out what's going on. And then we're actually asked meaningful questions. Okay, so let's talk our way through problem 4 here. Okay, so we have a practical current source this time, which is providing a certain amount of power to a particular load. So I'm going to draw a circuit here. So we have a practical current source. So some IS in parallel with some resistance RS. And then it's also connected to a load. While I'm at it, I'm going to draw a VL here. And IL here. And what we are told is some power corresponding to a particular value for the load resistance. And then the same practical current source provides a different power to a different load resistance. And from just these two pieces of information, we are expected to be able to figure out what IS and RS are. I think this is not necessarily easy, but fairly straightforward, right? So, for example, we know that P1 is going to be IL1 squared times RL1. Where IL1 squared using current division is going to be IS times 1 over RL1 divided by 1 over RS plus 1 over RL1 squared times RL1. And then we could use the exact same relationship and say that E2 is going to be IL2 squared times RL2, which would give us IS times 1 over RL2 over 1 over RS plus 1 over RL2 squared multiplied by RL2. And now, once again, we have two equations and two unknowns. So we should be able to solve for IS and RS. Once we solve these for IS and RS, we can now look at the rest of it, okay? So we're asked to find the values of RL, VL, and IL if VL times IL is at a maximum. So effectively, we need to find VL, RL, and IL when our power is maximum, right? So for part A, we know that sorry, let me see what's going on in chat here. Michael, yes, I was working on the exam earlier today and I lost track of time. So I got the lecture from yesterday edited, but I did not get it uploaded to YouTube because I finished editing it at 1:55. So I'll have it up within 5 to 10 minutes of me wrapping up this class, and then I'll post those notes as well. So both items will be up this afternoon. So for part A, maximum power transfer is going to occur when RL is equal to RS we're expected to solve for VL, IL, and RL. So we know that RL should just be equal to RS. IL in this case is just going to be 1/2 IS, and VL is going to be IS times RS over 2. For part B, we want our voltage to be at a maximum. So let's think this through here. If we want our voltage to be at a maximum, what does the value of RL need to be? Anybody have any thoughts?
You're asking what does RL, IL, and VL need to be?
Yeah, but so specifically for this instance, we want VL to be at its maximum. So we have to figure out what value of RL makes that condition occur. And then once we know what that value of RL is, we can solve for VL and IL.
Would we take a similar approach like we did with finding the derivative of?
I mean, I guess realistically we could,
Okay,
but let's think about things logically here and not have to worry too much about the calculus, all right? So if we want VL to be at its maximum, so VL is the voltage drop across the parallel combination of RS and RL, right? RS and RL are in parallel. And so that voltage drop is just the voltage drop over those two resistors. Okay. Are we okay with that sentiment?
yes, that's from when we derived the relationship earlier.
Sure.
Okay,
So using Ohm's law then, for VL to be at its maximum, we want the resistance of RS and RL in parallel to be at its maximum. So what is the absolute maximum value that RS in parallel with RL could possibly have, right? RS is a fixed quantity and RL is something we're trying to figure out.
would it be the value? So like if you were to go through and calculate the parallel between the two, would that value be what we're looking for? No, that doesn't sound right.
I mean, you're getting there, but you're trying to apply too much math and not enough intuition, in my opinion.
That's fair. No, yeah, I hear you.
Yeah. So what does it, okay, so if I have two resistors in parallel, right? It's going to be R1 times R2 over R1 plus R2.
Right.
So if
Right.
I want to make this quantity as large as possible where R1 is fixed, what do I need to do? Well, I want to make R2 as large as possible, right? So that my product will be larger than my sum. So the maximum value this could ever take would be R1, which will occur if R2 approaches infinity. So effectively, our load voltage is going to be at its maximum when our load resistance is an open circuit.
Okay.
And that's true regardless of what type of practical source we have, right? So what I mean by that is if I replace my practical current source with a practical voltage source, where this was IS times RS, and then I had RS, and here is RL, here's VL. If my resistor RL has any value that isn't an open circuit, my load voltage isn't going to be as much as it could possibly be. The maximum value it could ever have would be this VS or IS times RS. Putting a load resistor in that has a finite value is going to cause that thing to be smaller because this guy is going to have some voltage drop across it. Okay. So for this condition B, RL needs to be infinity, which makes VL equal to IS times RS, and it makes IL be 0 amps. So that's how we would maximize the voltage at our terminals of our practical source. Part C is the inverse of that. We want to make the current as large as it can possibly be. So if I have a current source in parallel with a resistance RL, and then I'm going to put something here, and the goal is to make IL as large as possible, what does that something need to be?
An open circuit, yeah?
So if I put an open circuit there, then IL will be 0. Is 0 the largest amount of current I could get out of this thing?
No, so it would just be just a wire.
Exactly right. So we'd need a short circuit.
Hmm. Yeah.
For part C, RL needs to be 0 ohms, which would make VL 0 volts, and it would make IL IS. So effectively, regardless of what we have connected to our practical sources, the largest voltage we are ever able, excuse me, the largest voltage drop we're ever going to be achieved, dang it, I can't talk today. The largest voltage drop we are ever going to be able to achieve is the open circuit voltage. And the largest current we're ever going to be able to achieve is the short circuit current, which is exactly what we figured out here. All right, let's see what problem 5 holds in store for us. This is just more source combination stuff. The only thing that I want to point out here, let's see. Over here on the right-hand side, treat these as if they were a pair of open circuited terminals. And so you're trying to combine all of this stuff down until you just have 2 elements and that open circuited set of terminals. Christopher, no problem. I'm about done anyway, because we've only got 10 minutes left of class. Yeah, so for this particular problem, I think it's fairly straightforward, but it's drawn a little poorly. In as much as it looks like this resistor R5 is kind of dangling here. But that is important. These are the open circuit terminals that you're trying to simplify everything to. So your goal in problem 5 is to reduce everything down to either a voltage source in series with a resistance connected to that open circuit set of terminals, or a current source in parallel with a resistance RS connected to that open circuit set of terminals. So very, very similar to what we did in class with those couple of different examples. So problem 5 is fairly straightforward. All right, I've talked for 100 minutes straight. So I'm going to stop talking now, and I'm going to work on getting that lecture video from yesterday up for you guys. I will still be on Zoom if you have any questions, though.
All right, thank you so much.
Yep. Thank you guys for your patience, and I apologize for the calculus mistake earlier.